And with that, now, thank you, we are delighted to have as our speaker this evening Gregory Chirikjian, Professor of Engineering at Johns Hopkins University. He will be talking to us tonight about the design, construction, and analysis of what have become known as self-replicating robots. Those robots that can make copies of themselves from spare parts. The issues are many, and he will be concentrating his talk this evening on the degree of environmental uncertainty that the robots can handle, and in particular, a measure of that uncertainty, entropy. He received his undergraduate degree from Johns Hopkins University and his PhD from the California Institute of Technology. Since 1992, he's been on the faculty of Johns Hopkins University and is now a professor in the Department of Mechanical Engineering. His research interests include robotics, applications of group theory in a variety of engineering disciplines. Maybe you can speak to us on that as well. And the mechanics of biological macromolecules. He's the author of over 200 publications. Greg Chirikjian.
What I will be talking about is entropy and self-replicating robots. Before I get to this topic, though, let me tell you a few of the other kinds of things that we work on in my lab that I actually won't be talking about. So the first part of the talk is not the talk. So I did my PhD about 20 years ago at Caltech, and at that time I was working on snake-like robots. And on the left we see a snake-like robot grasping an object and manipulating it, much like a caterpillar might walk over a log. And remember, this was 20 years ago, so the idea was we were going to use these snake robots to capture Soviet satellites from outer space, as in a James Bond movie. So that's how I started my engineering career. But as we all know, now the Soviet Union is no more and the Russians are our friends, so I needed to look at some other kind of business to get into. And so I got into modeling biomolecular complexes and structures as mechanical devices, as machines. So another topic that I've been working on is protein motions and functional motions of large biomolecular complexes. Another area that I work on is pure and applied mathematics. This happens to be the Euler-Poincaré equation, which is something having to do with variational calculus on Lie groups, which is an aspect of group theory, which the physicists among you, I'm sure, are familiar with. But again, I'm not going to be talking about any of that stuff. What I will be talking about today is self-replicating robots. And mostly I'll be talking about toy-like robots that were designed and implemented by my students. And these are graduate students, these are undergraduate students, and high school students who visit my lab over the summer. So I'm going to start with a little bit of history of the area of artificial self-replicating systems. I'm going to show a lot of movies of prototypes of these toy systems. And then I'm going to get into more of the analytical side, which is to discuss something that we call the degree of self-replication and the environmental entropy that these robots can handle. Okay, so to start with, I'm going to make a distinction between three things that often get put together in the literature. There's, on the one hand, replication. And so that's when a system is copied, but possibly with the help of some outside active agent. Then there's self-replication, which is where an agent makes a copy of itself from passive raw materials in the environment. And then there's self-assembly, and that's the case where there is no original, and things sort of come together on their own. Okay? Now, the distinction between replication and self-replication, so a cell, it would be self-replicating with nutrients, which are passive. The cell can copy itself. In contrast, a virus requires the machinery of the cell to perform some action, in order to replicate. So in my terminology, and I talked with Carl about this over dinner, we may disagree, but in my terminology, a virus is replicating, whereas a cell is self-replicating. The difference, of course, is the ribosomal machinery. In self-assembly, for example, if you put your cup of water in the freezer and it freezes, that is a form of self-assembly. Any kind of crystal growth would be self-assembly. So with these three concepts in mind, I'm going to be talking about the artificial self-replication. So robots making robots out of spare parts. Now this area goes back to the 1950s, actually, with the mathematician John von Neumann developing the theory of self-replicating automata. He never built anything, but he developed a theory for self-replicating automata that really built on the Turing machine concept in computing. And then also in the 50s and 60s, Penrose and Jacobson and others developed simple toy models that demonstrated some concepts related to replication and self-replication. And in the late 1970s, Robert Freitas picked that up with the idea of sending a factory to the moon that could scoop up the lunar regolith and make other stuff and basically bootstrap off of an initial investment and then have some kind of automated factory processing materials. More recently, a number of people in the robotics literature, including myself and the others listed here, have looked at modular reconfigurable robots, either with a homogeneous set of modules or a heterogeneous set. And also closely related to self-replication is the area of self-diagnosis and self-repair of a system using raw materials. And I'll talk a little bit about that. So here are some pictures of some of the various work that's been going on by others in the field. On the left here, this was actually published in Nature by a friend of mine, Hod Lipson at Cornell University, where he basically had 4 blocks stacked on top of each other to form an arm. And then that arm would go and pick up one block and place it down, and then pick up another block and place it on top until the 4 blocks got stacked. And he called that a self-replicating robot. And that led me to come up with this concept of degree of self-replication. Okay, so if one has 2 halves of a robot that are fully put together, and then a robot comes and pushes them together, and then the robot starts moving, one might say that's self-replicating, or one might say that's cheating. I don't know, but so on the other hand, if you have a cell which is taking in chemical nutrients that are very simple in their form and creating complex macromolecules out of it and then forming a copy of itself, that has a much higher degree of self-replication. So it's not an all or nothing thing. It's not necessarily this is not self-replicating and that is, but we can quantify, we can analytically calculate a degree of self-replication where putting 2 halves together has a very low degree of self-replication, and making something complicated out of some simple components that could have a high degree of self-replication. So these are some of the other efforts in terms of related concepts of blocks, block-like robots that can form complicated structures. And then the RepRap has been a sort of very popular thing. There are blueprints for making a system like this, which basically is a rapid prototyping machine that you can build at home. So as I mentioned, the history of self-replicating systems goes back to the Hungarian-American mathematician John von Neumann. He was also responsible for the development of the ENIAC at the first large computer at the University of Pennsylvania, which, by the way, when you say you have a bug in your computer, that goes back to the days when literally, if a moth flew into the computer and landed on one of the tubes and fried, then that would ruin the computation. So the computer bugs we have these days are not that literal, but can be equally impactful. His basic idea was to develop a cellular automata, a kind of computer program that had the ability to self-replicate. And in von Neumann's theory, there were four essential components. And keep in mind that he developed his theory before the Watson-Crick paradigm in DNA replication. And I say DNA replication, not self-replication, because you need various polymerase enzymes which need to be manufactured somewhere else for use in the replication process. So in von Neumann's paradigm, there were four components. A, an automated factory or so-called universal constructor. B, a copier that takes instructions and copies A. And C, a controller that switches back and forth between A and B. And D, the list of written instructions, which also have to be copied by the copier. So in von Neumann's mathematical paradigm, you start with one copy of A, B, C, and D, and then you get two copies out. Now, as an engineer interested in physical systems, I realized, and my students realized, that this picture is a little bit incomplete because you need some kind of raw materials if you're going to build physical robots going in. And we know from the laws of thermodynamics that you're going to produce some kind of waste in the form of waste heat or waste resources, materials, during this replication process. Moreover, in the context of robots, we think of it in terms of an initial set of robots, R, an initial set of materials, M, and an initial environmental state, E. And after the replication process, we have a new set of robots, presumably more robots if they're replicating, a modified set of materials, and a modified environment. And so the replication process is a function that takes the initial set in and over time produces the final set, and with more robots than you started. So this is a motivating example. This is a Lego Mindstorm set. It was used about 10 years ago in a class that I was teaching, and the topic of the class was design a self-replicating robot. Now, this is not a truly self-replicating robot because it's being controlled from the outside. But unlike von Neumann, my interest was on the physical side of the self-replicating system. I'll show you other videos later where it's fully autonomous and the robot is doing all of its own thinking. But I think this demonstrates a lot of the basic principles with a $100 set of Lego Mindstorm parts. So what's happening here is that the student is remote controlling this robot to put together a replica that consists of 5 parts. You just saw it assemble the chassis. And now this is a 3D picture. You're looking down from the top. It's manipulating this ramp. And this ramp has chopsticks glued to the end of it to make a little entropy funnel, so that, just like in protein folding, entropy funnel, so that now there's a loose sandwich of 3 layers in this robot. And then there's a cave over here with a slanted ceiling. And the original robot will ram this in there, thereby making the loose sandwich into a tighter sandwich where the electrical connections are made. And then the replica emerges from the cave under the same remote control signal as the original robot. Okay? So this demonstrates a few important principles, even though this is science on the cheap, which I think a lot of people are going to have to be doing in the foreseeable future, given the budgetary situations. But what you have here is an unstructured environment in the sense that there were a lot of parts scattered around at random. You have passive tools in the environment, and you have a way to reduce the environmental entropy so that the system can replicate. Okay, oops, we already saw that one. Here's another extreme. This one, by my former student Georgios Kalotsakis, this one, there is no remote control. This robot is simply moving around at random in a sea of parts. Okay? And it has no other goal than to make copies of itself. So it's just moving around at random, no care in the world, just bumping into whatever it bumps into. And these parts have magnets on them. And then every so often it'll bump, and then a full pizza pie will be made, and then voila, you have another robot. And now, of course, this starts a chain reaction, because whereas you had one robot before that was bumping around at random, now we have two that are bumping around at random, increasing the rate of auto-catalyzation of replication. Then soon we'll have more robots, and I think you sort of get the picture. Now, an interesting thing here is that more is not always better, because you can end up with incomplete pizzas if you have the wrong number of parts. And if you have one fewer part, you can guarantee that you will get more replicas in an averaged random sense. So in this particular case, we get 3 partial pizza pies that can't make replicas now, whereas if we had one fewer part, then we could have had more replicas. So the take-home message there is that more is not always better. Now here, this is again, with very simple parts, this is a completely autonomous self-replicating robot, which is going around and picking up parts and putting them together to form an exact functional copy of itself. Now, the program that's driving this robot, there's a program on board, but then there are visual cues. The robot is looking down and just following the line and reacting to these reflective pads. So this is sort of, you could view as sort of a metabolism, or as a, well, however you want to view it, as a transcription process, whatever. Whereas there was one robot to begin with, now there are 2 robots. Okay? But this is in a completely structured environment. There's very little environmental entropy here, whereas in the previous example, there was a lot of environmental entropy. So, and moreover, these robots had computers on them, and they're doing very simple tasks. So this is getting into the idea of what I call the degree of self-replication. If you have basic parts, if your input parts for your robot are very complicated, and the robot is doing nothing other than putting very complicated pieces together, most of the work went into designing and building the basic parts. So the degree of effort that the robot is doing compared to the degree of effort that went into making the parts is very small in these cases. And so what we did was we asked the question, can we do away with the computer, and can we put individual transistors, or what's equivalent to that, electronic relays, on, just a couple of them on each of these subsystems, so that we don't have a concentration of the complexity in the computer. We have very simple computing, and it's distributed over all of the parts. And then can we make a robot that does these same sort of behaviors, but with very simple parts? And so the brain of this robot was very simple, just a few electrical components that were spread over all of the pieces. And so this actually, it does the same thing as what I showed in the previous slide, but with no computer. So it has sort of a higher degree of self-replication because the basic input parts were lower, and it does the same output. So how do we analytically measure how complicated a robot is and what this degree of self-replication is? I won't go through all of this, but I'll just show you with a very simple example. Suppose that I have a robot that is like an automobile, and it's almost completely put together except the wheels have not been put on. Okay? That's one scenario. And then let's look at another scenario where maybe the chassis is put together, but the drivetrain and the differential, the axle, and the tires are not put on. Okay? Obviously, more effort is required to put all of this together to get the whole thing than in the case where you just have to put the wheels on. Okay? And so what we can do is we can assign complexities to each part. And one measure of the degree of self-replication is this very simple thing here, where we look at the ratio of the maximum complexity of the most complex part to the simplest part, and we look at the average complexity. And this product is what we call the degree of self-replication. And if we say that wheels are relatively simple compared to a transmission or compared to an axle, then the degree of self-replication in this case is better than in this case. Actually, so I'm sorry, this is the degree of complexity, and our degree of self-replication is the reciprocal of that. So here, low means good in the sense of being more truly self-replicating, and high is bad. And so, but then the question becomes, how do you assign complexity to parts? And when it comes to, what are the most complicated parts? Well, the structural parts are not complicated. It's the actuation and it's the computing parts that are complicated. But we can assign complexity in a uniform way to both the computing and to the actuation. And how do we do that? Well, if you think, what is an actuator? It's something that causes motion. And the most basic kind of actuator is a solenoid, basically a coil wrapped around an iron core. And if you look at what is the most basic computing element, well, it's a transistor. Well, every transistor is equivalent to 2 relays. And what's in a relay? A coil, okay? So we can relate the complexity in a computer and the complexity in an actuator by basically counting coils or counting the equivalent of coils. So that's one. So we have 2 sort of dimensions to how we measure how truly self-replicating a system is. One is this degree of complexity of the parts relative to the whole, and the other is entropy, as in the title of the talk. So, and the entropy comes in terms of characterizing how ordered the environment was. The robot that follows a track and every part is pristinely placed in advance, and the robot just picks up those parts and puts them together, that handles a much lower entropy than the robot that can handle parts at random positions and orientations in the environment. So this is the general form. This is Gibbs' formula for entropy from statistical mechanics. And in fact, that's what we will use when we describe entropy of parts in the environment. But first, I should mention, entropy is also used in the field of information theory as developed by Claude Shannon. And this was around the same time as von Neumann, and the two actually knew each other. And of course, entropy in statistical mechanics goes back, way back to Boltzmann's H formula. Basically, entropy increases in thermodynamics. Shannon was developing the modern theory of communication. How much information can you push through a communication channel? And the logarithmic definition of information, it follows the same entropy formula. So as Lohr has it, Shannon and von Neumann talked to each other. And Shannon said, well, I have this formula that describes how much information you can send over a channel, and what should I call it? And apparently von Neumann, and again, as Lohr says, von Neumann said, well, you should call it entropy. Number one, because it has the same mathematical form as entropy in statistical mechanics. And number two, nobody really understands entropy. And if you call it entropy, you will win every argument because nobody can argue against you. That's how the story goes there. So the entropy that we are using is really a hybrid between statistical mechanical entropy and information theoretic entropy. In statistical mechanics, the domain of the functions are generalized coordinates and conjugate momenta. We are not dealing with momentum here. Our parts are static in the environment. This is really a conformational entropy. It's an entropy of parts. What are all the possible configurations of parts in the environment that are possible? And from among all of those possibilities, we can calculate the parts entropy. So if the robot can function, no matter how you put the parts down, then this is the entropy that it can handle. Okay? And so in the sense that we don't have conjugate momenta here, it's sort of like Shannon's entropy, and it's really in the middle of the Shannon information theoretic entropy and the statistical mechanical entropy. If the parts can be put down in a sparse environment where they don't interact and you can treat each one as independent, then the entropies add. If the environment is very cluttered, then that's not true anymore, and then things become more interesting. But at the end of the day, one measure of the degree of self-replication of a robot, of a self-replicating robot, is how much entropy change can it enable. And again, this is not thermodynamic entropy because, of course, thermodynamic entropy is always increasing. If you measure the battery state of the robot before the process and after, et cetera, you'll get an increase in entropy. But we're only talking about the configurational entropy, the parts entropy. And of course, if you start out with a lot of parts randomly positioned in the plane, and then you end up with robots that are all connected together, your parts entropy will decrease in a self-replication process. So this is just saying you subtract the initial from the final, and that gives us a degree of entropy. So to demonstrate this, here's a picture, and I'll show a video later of this robot, where this robot is also following tracks, but it can also go off the tracks, and it can bump into various landmarks that are off the path to get it situated correctly. But the take-home message is that there are 6 stations here where the robot picks up parts from. And this particular robot can only handle a very discrete kind of entropy, which is very much like the information theoretic entropy. And this basically is the permutation of the locations of the parts. So this robot can function if the parts are at any of those 6 locations. So you have 6 parts. There are 6 different locations, so there are 6 factorial, different places, different arrangements of parts that this can handle. That's all it can do. It cannot handle the case where things are positioned and oriented at random, although we do have other robots that can do that. And when you have this very simple discrete case, it's very easy to calculate the entropy and get a number. So this robot can handle 9.49. Okay, that's how much entropy it can handle, whereas the first track following robot that I showed you can handle only an entropy of 0, basically. The parts had to be exactly in the right positions and orientations. So I'll skip some of that. And then I'm going to talk a little bit about a related topic, which is robotic self-diagnosis. In teams of robots, how can a team of robots diagnose if one of its members is not acting correctly? If there's a fault in it, if it has some kind of bug, and the robot, it needs to be diagnosed and repaired. And so, again, we have these toy robots. They have different patterns on them so that they can be seen from an overhead camera. There's a right and left wheel assembly, a front gripper, and a main chassis. And for these very simple robots, we figured out all the things that are likely to happen. So the right wheel might slip, the left wheel might slip, the right motor might burn out, the left motor might burn out, the gripper might stop functioning. And from all of the things that we observed could happen, we came up with a set of maneuvers, a diagnostic dance that a robot that's undergoing a diagnosis has to undergo this dance while the other robots watch. And from the way the robot moves during this dance, the other robots can ascertain what is wrong with that robot. Or maybe that robot is fine, okay? And then each one of them may have a different opinion, and then they have to vote. And the vote could be, the robot's fine, leave him alone. The vote could be, this part needs to be replaced, let's go in and replace it. The vote could be, he's too far gone, let's throw out all the bad parts and cannibalize them and keep just the good parts. There's all kinds of votes that could happen. And so the pictorial, and it's always a probabilistic decision. So there's observations, there's errors in those observations. There could be some dirt on the floor, so the robot's wheel slips even though the robot is perfectly fine. You never know. So it's always a probabilistic decision process where the robots in question have conditional probabilities. They condition their answer of their diagnosis on the observations and on prior models of all the possible things that can go wrong. And This is just a picture of the internal process. But the picture basically looks like this. You have three neighbors here. There's the one being diagnosed, and the one being diagnosed sort of does a little dance that changes its position and orientation, and then the ones making the diagnosis formulate some measurements and make a decision based on that. So this is not the end of the talk, but this is the end of this part of the talk. So I'll just say that we have a descriptive framework for measuring the degree of self-replication and the complexity of constituent parts in self-replicating systems. We've built a number of toy-like prototypes that we use to develop the theory more, and it gives us a path. So we want in the future to move in the direction of higher degree of self-replication in the sense of more and more parts of simple nature being put together to make more and more complex robots that can handle greater and greater environmental entropy. And so, and merge that with the diagnosis side of things. So, for example, you could imagine robots not only diagnosing and repairing themselves, but the structures and environments in which they live. So this was a video that we put together a few years ago. So far, the Navy does not want to shower down any money on me, but I'm hopeful for the future. Okay, and then in the far future, maybe the far, far future, one could imagine, like Robert Freitas's vision from 30 years ago, sending some kind of factory to the moon, and all of the parts have the ability to then scoop up sand, or the robots have the ability to scoop up sand and do some materials processing and build from raw materials other robots. Now, keep in mind, this is actually a more ambitious goal than life, okay? Why? Because no living thing can scoop up sand and eat it and replicate, okay? If we could do this with robotic systems, it would be something that is, in a sense, I won't say more ambitious, but let's say, I don't know what I want to say. It's not more difficult than life, but it's using more basic resources than what life uses to produce replicas. So this was all done by my students, and one student in particular, Matt Moses, I'm going to show his work, and his work, it's all videos. So his PhD dissertation was last August, and I basically borrowed his movies, giving sufficient credit here, the work of Matt Moses. This is his work. And I'll just start this out, and then the questions can start as this is playing. But I'll just set this up a little bit. Matt was interested in desktop self-replicating systems. And so he made this robot. So this robot is made out of all of the same basic components. They are these plastic blocks that have cones on the top, and they have conical holes in the bottom. And so these parts, if you just drop them from a few centimeters height, they will just fall into the right place. They are designed to handle conformational entropy. You can be off a little bit in the angle. You can be off by a couple of millimeters in each of the x and y directions. And what that does is it makes it easy for the robot to put these parts on top of each other. Okay? It's because the robot is designed with this entropy funnel idea in mind. Okay, now all that's being demonstrated here, and keep in mind that was 3 years ago, is that the robot is placing and then screwing together a stack of 3 of these parts from which the whole robot is made. Okay? And I told Matt, if you do that so that this robot can make a copy of itself, that's worth a PhD. And maybe, given that our friend Hod Lipson stacked 4 blocks and got a Nature article, maybe if you do it for 150 parts, maybe we'll be in the running also. So he decided to design this. This is Matt's structure. It has a bridge on top. And you can see it working in simulation here. So it has this bridge on top, so it's basically an XYZ platform. We needed extendable legs so that this could lift up and down. Okay, these towers are telescoping. And then this can move in one direction. Then the tower goes up and down, and then over here it goes left and right. And then this is the end effector, the gripper, that picks up parts and places them. And so this is a simulation of Matt's vision of essentially like an artificial ribosome. Okay? There are basic blocks over here, which would be like the input amino acids and the residues. And over here, it comes over here and it reorients the parts. And then it's picking and placing. Now, the whole set of parts, there's about 150, but the number of operations required is over 1,000. 1,000 pick and place operations to take this initial set of blocks and to make a copy of the actual robot. Okay? And so I said, Matt, if you do that, that's definitely worth a PhD. And so he did it in simulation. And then I think, actually, I don't know how to speed up this simulation, but it would take about an hour. I don't think you all have that much patience to go. So what I'm going to do is I'm going to show movies of snippets of the actual robot, okay? Not a simulation. But this is, he made these 150 parts. And when I say make, I don't mean he went out to the store and he bought them. I mean he made molds and he poured plastic and he made those parts from raw materials. If you consider liquid plastic as a raw enough material, he made those parts, okay? Now, another aspect of this work is how to get the robot to make the parts. And I'll show you about that in a minute. And how do you get the robot to make the motors that drive the next generation of robots? So this is just showing snippets of the individual steps. So the end effector works, the gripper works, by coming down, having the pegs fit into the right holes, and then there's a screw mechanism that screws into a part and then picks it up. And then it places it down and unscrews, and then it goes down and then screws that part into the right location. This is from another view, how the parts connect. It's the two towers. Again, you'll see the whole robot from a different viewpoint in a moment. But this is a very different, now how does this relate back to what I said before? So here you can see the screw mechanism screwing things into place. The amount of entropy that this can handle is actually relatively small because the initial set of blocks are palletized. They're in an ordered state. You're just going from one ordered state to another ordered state. So you could call this an isentropic self-replication process, to give it a name. Although there is some finite permutation aspect to how the original parts can be situated, but there's no sort of arbitrary orienting of parts in a box and the robot finds the parts and puts them together. But this is high on the level of degree of self-replication in the sense that the individual parts are all very simple and the resulting robot is quite complex. So this is showing, this is sped up by, I think, a factor of 2 or a factor of 4. But there are no hands coming in and out of the picture. This is all done by the robot on its own. And, and we can see, again, it takes hours and hours and hours. But he designed a system which is very tolerant to faults. And it all has to do with this cone and this conical peg design, which enables us to do complicated pick-and-place tasks with fairly simple devices. And this is still a relatively simple robot, even though it has many, many parts. So this is just showing various aspects of putting different parts down. Oh, I said you could ask questions. I'm sorry. So if people want to ask questions, there's just more and more. I mean, his dissertation defense was wonderful. It went on like 45 minutes of these videos. If you ask me questions, the videos can be playing in the background, so I'm happy to take questions.
Those motions, motors moving up, down, screwing, etc., are they like electric motors?
Yes, they're simple DC motors.
So those DC motors are not plastic parts, right?
That is correct. And so what you can think of as what I'm showing you here is really like a child's connect the dot coloring book. We are putting the dots down. Okay, originally the page is blank. We are putting the dots down. So one dot is how to measure self-replication. Another dot is how to design the physical structures that enable a robot to put parts together. We are connecting, we are putting the dots down. We are connecting some of those dots, but there are still wide open for many dots to be connected. And one wide open area is how to design motors so that they're easy for the robot to construct and then use in the future generation parts. And so, in other words, we want to increase this degree of self-replication. So the motor has a certain complexity to it. We count that complexity when we assess the degree of self-replication here. If we can go further and reduce the motor down to more basic parts, then we increase the degree of self-replication. Okay? And I'm not saying we're there yet. We're not at the level of picking up the sand yet. But I'm showing you dots in that direction. And connecting those dots may take a very long time. Yes?
Can this handle a bug?
It depends. If it's a smart bug that gets out of the way before it gets squashed, then, then yes. How brittle it is, how sensitive it is related to how little entropy this robot can actually handle. So we're moving in the direction of a higher degree of self-replication and higher degree of entropy handling. This particular one doesn't handle a lot of entropy well, but it has a lot of low complexity parts.
Does it have the ability to unravel what it's done if it detects an error? It took a little while to emerge?
So currently, this is open loop. But I have a very talented master student who's working on closing the loop. So in other words, if any of these parts are not placed correctly, it will not work. It will stall the system. But what the new student, his master's thesis is going to be is to take Matt Moses's masterpiece here and add feedback to it to add robustness to the process. And so if a part it doesn't get put down correctly, then take the part out and put another one in. And various levels of feedback inside.
You want to give him a PhD too? Or improve on the
Well, if I can keep him around long enough. But people have their life plans, and some of them don't involve PhDs, and some do. So I'm happy to bring in as many people who want to do PhDs as is humanly possible. So this is showing some other. So this is basically showing the different parts, like building the towers. In this case, building the track. Building the bridge part that goes across the top, how to place the bridge part. It was all worked out in simulation, and then he demonstrated all of the different steps that were the critical paths in this replication process. Yes?
I'm not quite sure how it could be integrated into this, but when I see anything like this with small plastic parts, it makes me think of probably know about the MakerBot machines.
MakerBot.
It's a computer-aided, small computer-aided design machines that can produce in 3 dimensions small plastic parts.
Uh-huh.
Just,
Oh, you mean like rapid prototyping machines?
yeah.
Yeah, sure. Uh-huh.
It makes real 3-dimensional
Right.
from design software.
And that, in a sense, the RepRap that I showed is sort of in that vein. The difference between that kind of work and self-replicating systems is that typically a 3D printer is not made out of the same materials or parts that it's producing. And so it's closing that loop is the challenge that we were trying to address, which is not addressed in work like that.
Anecdotally, when the Mars Society
like the laser or, yeah.
Apart from that.
Okay. Well, I mean, there, you know, if one does not limit oneself to being a purist, you know, you can say, well, let's say that there are certain vitamin parts that we're not going to try to reproduce, and let's just try to reproduce the whole rest of it. So if you want to send something to the moon, you can use 99.9% of your mass from the local resources, and you send a few microprocessors and lasers and other things, and you still get the benefit of not having the heavy launch requirements.
So Greg, for this prototype, what is the impact of extreme temperatures as is? This is a room temperature.
Yes.
Higher or very cold?
So under extreme heat it will melt, and under extreme cold it will become brittle and freeze up.
So what's the range?
We have not tested that, but this, we would not send this particular one to the moon. No, this one is only for the laboratory to demonstrate basic principles. FAO Schwartz. So, yeah, well, that's. I think we saw something very similar to this already. I will get to at the end of Matt's dissertation defense, the discussion of how to have robots design and print, not design, but to print motors is there. And I will show you that, what we've done. And we published this in a conference last August, actually. Yes?
How do you think, or how would you compare this to using molecular organisms and taking a more nanotechnology approach? Using living material and starting small.
So most of what I have seen in the nanoscale falls not under what I characterize as self-replicating systems, but either as self-assembly, like what George Whitesides at Harvard University does, or my colleague David Gracias at Johns Hopkins does, whereby you design parts and maybe you paint them with a chemical coating and then throw them into a soup so that they, by surface tension forces, they coalesce in a predefined way, right? There's no original there. There's just a bunch of parts that have been designed to facilitate self-assembly. And similar is true for DNA tiles, where you basically have a very small, painted with a little bit of DNA and then a complementary DNA on the other side, as in what Eric Winfrey at Caltech and what my new colleague Rebecca Schulman at Johns Hopkins does. It's a similar kind of thing of what I call self-assembly. And then at the nanoscale, you know, the idea of replication, but not self-replication. So I make the distinction, where is the energy being transduced? Is the robot taking action to produce a copy of itself, as in a ribosome metabolizing ATP to make, you know, replica proteins? Is energy being metabolized or not? And if it's just a matter of the environment, the stars are aligned in the right way and things coalesce, I don't call that self-replication. So within the context of your question, if you're asking me what is the role of self-replication versus replication and self-assembly, I would say this has a role at the macro scale to exploit resources on planetary bodies and other things where you actually want a specific goal to be done at the macro scale, whereas the other techniques or technologies are more applicable at the nanoscale and micro scale.
But they could be combined?
They could be. You could have a robot that takes some parts and puts them in a soup, and then that makes a complicated part, and then it gets its net out and takes the part out of the soup and then uses that part. They certainly could be combined. Yes, ma'am.
The robot I have in mind, the molecular robot, is the combination of kinesin and actin working on the tracks. And it would seem to me that would be easy for your students to reproduce.
Well, in a sense, this is like an actin-myosin, right.
Like you almost start to label the parts.
Well, you know, things in nature and in engineering sometimes, engineering mimics nature. Sometimes engineering comes upon the same answer as nature. I mean, the ATP F1's ATP synthase is just like a stepper motor, but the stepper motor was not designed with that in mind. There's just a certain way of doing things, right? I mean, you know, DNA is a helix, but the vine that grows up the tree is a helix, and you know, when the pharaohs wanted to build pyramids, the path that the slaves took were helical up the hill. There's a certain way of moving things in three-dimensional space, which is not unrelated to group theory, that is just the natural way of doing things. And sometimes learning from nature facilitates that. Sometimes we stumble upon the similar ideas on our own. And sometimes, like space travel, nature doesn't have, there's no jet engine in nature, right? There's no ramjet or rocket engine in biology.
Well, I might disagree with that. When you see the flagella organize themselves to drive the E. coli,
Uh-huh.
then it seems to me that's a metaphor for it.
Well, of course, there are many metaphors, and it's a matter of how much you want to stretch it. But if you say burning liquid hydrogen with liquid helium, and if that's what I'm calling, with hydrogen and liquid oxygen, then if I call that a rocket engine, there's no, direct in nature.
Yes, there are many ways to come up with a fundamental set of basic pieces. For example, if the pieces are all instruction sets and you have an instruction that will repeat another instruction twice, another set of instructions twice, one that will be repeated 0 times, one that will compose 2 sets of instructions, one that will transpose 2 sets of instructions, that's a complete basis for all computable functions.
Mm-hmm.
Of course, it's a jungle because you can do anything with it. If you have another basis, how do you compare the entropies for the 2 sets?
Well, you're talking about the computing aspect, and so, von Neumann and the computing aspect and the Turing machine, all of that, our goal was somewhat different. Our goal was to, because there are, computer viruses that replicate. There are various cellular automata, screensavers on your computer that the patterns replicate according to certain rules. Our goal was to focus on the corporeal aspect, the physical, hardware, mechanical aspect of the self-replication process. And within that context, we can use various computational paradigms, but that's not where our emphasis was.
Well, you have one set of pieces, you build something from, you have another set of pieces. You could build the same thing from each set of pieces. How do you compare the 2 bases?
Well, you couldn't necessarily build exactly the same thing from different pieces, right? I mean, it wouldn't be exact. It might, maybe on some macroscopic scale, it would look similar, but you couldn't build exactly the same thing if you were using completely different pieces. I mean, like, if instead of these cones, if I used square pegs, then actually the system would not work. And one could imagine a different paradigm in different parts, but in a sense, the proof is in the pudding. People have been talking about self-replicating machines for a very long time, but nobody's actually built them. And so the question is, why is that the case? And our answer to that is that because it's hard to get things to work, and the reason why it's hard to get things to work is environmental entropy, and that's where our emphasis has been. Yes, sir.
One nice example of just how much of a role environmental entropy can play is to look at the system of chemistry within a quasi-cellular medium. In case A, the molecules are simply randomly distributed.
Mm-hmm.
In the sophomore year chemistry formulas. And so the collision time between 2 molecules is determined by their distance and their fluctuation level. Whereas in scenario B, you have the microtubule, which attracts some of the chemicals.
Mm-hmm.
And the
Yes, I mean, so the design of filamentous structures and random motion in one dimension as opposed to three-dimensional space is used by biology significantly. In our case, at the macro scale, in the absence of some exciting Brownian motion or soup, we have much less thermal agitation, and we have a much more deterministic system. And so the design parameters are somewhat different than in biology and at the nanoscale.
Just going back to the sort of mind and body aspect of this, where are the instructions for this machine housed? How are they copied? And what sort of coding mechanisms are there for sort of errors that occur during the copying of instructions?
Right. So that relates back to the issue of the corporeal focus of what we are working on. Here, actually, the instructions are on an off-board computer, and the same off-board computer can run the replica and the original, and a computer can easily copy the files and send it to another computer. So we haven't focused on that. We focused on the mechanical difficulties. But in computing paradigms, that is handled, and other people who look at, for example, artificial virtual self-replicating systems address those sorts of issues. And we can sort of stitch the pieces together as needed, when needed. But for example, if we talk about the case of in situ resource utilization on the moon, it doesn't actually have to be autonomous, and the instructions don't actually have to be sent. You could remote control the thing from Earth as long as you have a physical presence there that can make use of the physical resources.
I think it would be fun if you showed a video of where it goes amok, where the AI instructions have positive feedback. And that's a metaphor for our current Congress.
Oh, well.
The whole thing goes amok and it doesn't work.
We have plenty and plenty of bloopers, but if I showed the bloopers, I'd get, at least in Baltimore, I'd get tomatoes thrown at me. So I decided to edit the bloopers out. So actually, I gave a similar talk at at one of the local society sections in Baltimore, and they were quite disappointed because they thought everyone from Johns Hopkins University should be talking about surgical robots, and they wanted to see their blood and guts right after dinner. And I disappointed them in that regard. So, I guess we have a different audience here. So, and then so just sort of to summarize all of this, the idea is that once you make, you start out with one of them and it extends the track, and then it makes a copy, and then it makes a copy, and then you could tile a wide environment as long as you have enough basic resources, but then that begs the question of how do you get your basic parts. And so part of what Matt did, what I've shown you so far is what we call the assembly side of self-replication. There's also the fabrication side, which is how do you take the raw materials and make the basic parts. And so there are a number of people who have looked at how you take basic materials from the environment and produce refined parts. And in fact, you could view the whole of human civilization as sort of self-replicating in the sense that you dig up ore and you refine it and you plant seeds and you grow food, and then you have supermarkets and highways, and then everything sort of builds up with people as part of the constituent parts of the whole self-replicating society. And so here are sort of the basic fabrication steps. There are basic molds. The plastic gets poured in, and then you get parts out. And so then the question is, could the robot do that, or does that have to be done by hand? And in fact, the robot can do many of these steps. There are a few, and another thing that the robot can do is the robot can print patterns. And once you have the ability to print patterns, if you can print those patterns in a conducting material, then you can make a motor. So this is actually a very poor motor, but it demonstrates the idea. So there are coils, much like this, that are sitting at every other place in this stack. And they produce very, very little torque, but when you stack them up, you get a motor that produces a significant amount of torque. And this motor was actually, these coils were actually printed by the robot. It was actually printed by a RepRap robot, but any robot that can do pick and place, including our robot, can print coils like this. And these coils were printed with solder material, the same material that you use to solder a circuit board together, which are not good because they have a low temperature melting point. And so, if you run this motor long enough, it basically melts down. But then we decided to go a little bit fancier. And so Matt did the same pattern, but on a printed circuit board. And then we made this very reliable motor printed with it has a simple 2D coil. So when we think of motors, we think of a sort of a thing with soft iron core and coils wrapped around it. The motor actually can be a simple printed coil in the plane and have the magnets orthogonal to that plane, and we can get torque out of that. So that's a motor that we published last August at an ASME, American Society of Mechanical Engineers designers meeting. So we can think about other raw materials, there's a lot of room to connect the dots, as I mentioned before, including a lot of these fabrication steps, how to make the robots more reliable, how to handle more environmental entropy. And here's a little connection between group theory and entropy and putting parts together. So if you want to take a part and stack it on top of another part, then all the complementary faces need to mesh. And we can write down in a formula, and this involves an integral over the group of rigid body motions with respect to the bi-invariant Haar measure for this group, of probability densities of where the parts are versus the shape of the domain of attraction of the parts. And we can write down, we can get as theoretical as you want to get in terms of writing down fancy formulas to compute basically how easy is it for two parts to mate. And so I'll leave it at that. I do have more videos, but I'm happy to answer more questions as well. Yes, sir.
Speaking to the last slide, as luck would have it, Dyson once conjectured that there were a nice, really intelligent species in the galaxy on the scale of perhaps 10,000 years. It could equip a large chunk of the galaxy with self-replicating robots. And if we don't see the robots, there are no intelligences. Are there any rate-limiting steps at the analysis that you're looking at with the group theories and the various juxtapositions of parts? Can you put some meat on the bones of Dyson's conjecture?
Well, let me back up and say I read Freeman Dyson you're talking about, right? Freeman, not Dyson the vacuum guy, right? Okay. Freeman, I read his book on the origins of life, and I found it very interesting about how he felt that basically vesicles and agents that inject themselves into vesicles are the beginnings of things. Other people have other ideas about that. I had a conversation with Jack Stostak about that, and he has other ideas. Now, I haven't actually read Freeman Dyson's book on the topic that you're alluding to. But these robots are not going anywhere fast, I'll put it that way. And if you want my ideas on the possibilities of intelligent life out in the galaxy, I'm happy to give them, although I'm no expert. But maybe that's better done at the social hour afterwards. And not broadcast over the internet. So.
You started your talk by showing this Lego Mindstorms, which is this nice general purpose set of blocks for building stuff. Are there any bits of research on finding sort of general purpose blocks for building anything? What do these sort of things look like?
Like a universal constructor. Yeah. Part of the difficulty there is when one says, I want to build anything. That's a pretty unrestricted set. And if you start to say, I want to build anything that does something, that narrows it down. And we narrowed it down by saying we want to look at parts that make it easy for the robot to make a copy of itself. And you say, why make a copy of itself? And the answer is that that keeps us honest. That keeps us honest because closing that loop is the hard part. And if we said, well, I'm not going to build a robot that builds itself, but I'm going to build a robot that builds another robot. Well, then how do I know that the robot that it's building is as complicated as the robot itself? Maybe it looks as complicated, but maybe it's not as complicated. So by focusing on the robot being able to make a copy of itself, we know that it's building something at least as complicated as itself. Now, and so with regard to your question, I think it's not defined to say to build anything. And one needs to rein that in a little bit and put quantifiable bounds on the set of things that you want to build. Then it starts to become possible to formulate what a universal constructor means in that context. I mean, in terms of like the Turing machine, with the tape and the writing dots on the tape, that was never meant to be a functional computer. That was, but it can compute anything, right? But it's really more like a metaphor for completeness in computing. And so if one is looking for metaphors, I'm sure one can find metaphors in self-replicating systems, but if one wants something that actually works, then you have to roll up your sleeves and actually settle on a specific set of parts, see what it can build, see how you can modify that set of parts to increase the set of things that you can build. So you can either view it from a top-down or a bottom-up perspective, and we were coming sort of from a bottom-up perspective.
It's still going back to what you started with von Neumann. I mean, obviously, when they were thinking of something that would mimic life, then you say, well, what's a characteristic of life? The living system can reproduce itself. So that was one of the concepts. If you're just talking about a cellular automaton and not restricting it in any way, you can find extremely simple examples, of cellular automaton with the right rules, where you can get a very simple pattern of 3 or 4 dots, which then reproduces 3 or 4 dots in the same configuration. But it's quite uninteresting. I mean, what made, and von Neumann came up with this extremely complicated example, as you mentioned, it's quoted, 29 different states for each cell. I mean, the interest there, as you said yourself, was it was connected to Turing. In a sense, he had a tape going in, which, among the other instruction sets, was an instruction set which led the thing to reproduce itself. But if you put it in another tape, it might reproduce something else. Whereas then if you get to Conway's game of life, even though they proved a long time ago there's a universal constructor, it's only recently anybody's shown possibly an example of that. But so the question is, it seems to me that the really relevant thing here, when you're talking on the broader scale, you're talking about human cultures and so forth and so on, is it's not so much the fact that you've got a replicator, but you've got a universal replicator. In other words, you mentioned this was before Crick and Watson, but the idea of the DNA is the fact you've got the same machinery underlying, almost all of life that we're familiar with. So you're back to that universal thing. It's not just that you have one thing that was ever created with DNA that created just that one thing and reproduce it. It's the fact that basically you're looking at something that people view as programmable. In other words, you've got the code depending on which particular DNA for which life form you're talking about, and then you've got machinery and so forth and so on. It can be very similar across the board. So you sort of, and just the last thing, because Robin says I never get to the question. So you guess what the question is. But the thing is, when you talk about the machines, it's an interesting observation that all the machines that are in existence today, if you're talking about large-scale machines, were built by other machines, maybe with human intervention today, often with just robotic intervention. So actually, any existing machine today, aside from something kid builds on a tabletop with some wire and, like say, an iron thing, actually goes back to the machines in the 19th century. I mean, there is already a whole living biological world of machines going on, which, with human assistance, has genealogies and everything else.
Well, I think you're basically saying in different terms what I said before, which is that the whole of human society, including highways and farms and supermarkets and everything is a self-replicating organism, including the technology. So, so I think that many of the things that you said were different ways of articulating what I was at least trying to say.
Actually, 40 years ago, we had two games. One was to write a program that would copy itself. The other was to write a program that would zero everything. And that was actually harder. There were only some machines where you can actually zero all of memory and leave nothing on it. Perhaps our society is more like that than like the self-replicating.
Well, I won't comment on that, but I will say that thermodynamically, erasing information takes more than writing information. And so when one talks about the thermodynamics of computation, that is a huge issue.
So thank you very much. Please join me in thanking our speaker.
Oh, thank you.
Appreciate it very much. And now a few concluding announcements for this portion of the meeting. If you dined with us tonight, had dinner with the speaker, and have not yet settled your account, if you would see our